In today's lecture, we're going to be talking about reading and interpreting phase diagrams. Phase diagrams are a plot of pressure versus temperature overlaid with a plot that shows which phase of a pure chemical compound predominates, is most common, or is most stable under a specific set of pressure and temperature conditions. And so phase diagrams are a kind of graphical tool that combines everything we know about the phase transition behavior of a pure chemical compound. Any pure chemical compound that exists and you can work with will have some sort of phase diagram that you can find in a reference book or on the internet that will describe what we know collectively about under what conditions the chemical goes from a solid to a liquid to a gas, solid to gas, etc. And it combines all this information on a single graph plot that if you can interpret, you can always use as a reference to give you a good idea of how the chemical is going to behave under specific sets of pressure and temperature combinations. And so phase diagrams are incredibly useful for chemists, physicists, and engineers to predict how a chemical is going to behave in a certain application. Whether you're interested in how the chemical behaves in a low vacuum environment like space, or you're interested as to how the chemical is going to behave at low elevation versus high elevation, or under extreme pressure, like in a heavy machinery application or drilling for oil or natural gas. So first, we're talking about how a phase diagram is put together and the types of information that you can get immediately from any phase diagram that you look at. In our phase diagram to the right down here, this is a phase diagram for water. This phase diagram describes the physical states of water at different temperatures and pressure and indicates under which conditions you're going to get a phase transition from solid to liquid or liquid to gas. So notice first and foremost how this phase diagram is laid out. As I said on the previous slide, pressure on a phase diagram is almost always on the y-axis. Temperature is almost always on the x-axis. The units that are used to represent pressure and temperature can vary, but usually you'll see pressure in atmospheres and temperature in degrees Celsius, but you may see temperature in Kelvin and you may see pressure in millimeters of mercury or other units. The pressure scale is often shown kind of non-linearly because the phase diagram is designed graphically to illustrate how the pure compound is going to change phase over a wide array of pressures or temperatures. And so as a result, you might see a little bit of manipulation of the y-axis where it seems like two pressure points are closer together than they ought to be if the scale was actually laid out linearly. And it's like they've shrunk sections of the phase diagram to make it fit on a single panel and still preserve the quality of information. Kind of like a specific type of projection of a world map, like a Mercator projection. They're manipulating the dimensions of the phase diagram a little bit to make it all fit in a single panel and be a little bit easier to read. The way you read a phase diagram is essentially to choose a pressure and temperature combination you're interested in, like 1 atmosphere of pressure and 100 degrees for water, which would be water's normal boiling point. And you plot that as a single dot on the phase diagram that corresponds to the temperature and pressure combination that you're interested in and see which phase of matter you land in under those conditions. It's not surprising since 1 atmosphere of pressure and 100 degrees Celsius is the normal boiling point of water, that if we look at that point on water's phase diagram, you should see that that dot is between the liquid and gas phase, and that indicates that water vaporizes under those conditions. So in addition to the pressure on the y-axis and the temperature on the x-axis, what you'll see on a phase diagram is solid black lines that divide the panel that is the graph into a series of different phase regions. In the case of water, the solid phase is on the left-hand side, the upper left-hand side, the liquid phase is in the middle, and the gas phase is in the bottom right. There's also a fourth phase, which we'll get to up here, indicated as the supercritical fluid, which is a state of matter that we don't usually see under normal atmospheric pressure and temperature conditions. But the way a phase diagram is made is essentially you overlay a plot of which phase predominates at a specific set of pressure and temperature conditions over a two-dimensional plot of pressure versus temperature, and then you read the behavior of the chemical by sliding two different pressure and temperature combinations on the graph, and it will show you what state of matter the chemical compound should be in at a specific pressure and temperature combination. The black lines that divide the phases are what are known as phase boundaries or phase equilibrium boundaries. They show you the conditions under which your pure chemical should be transitioning between phases. So if you're looking at a pressure and temperature combination that lands you on one of these black phase boundaries, you are going to be looking at a pressure temperature combination where a phase transition is happening to that state of matter, or you have an equilibrium, a kind of balance where the two phases of matter are present. Equilibrium is a concept that we'll talk about quite a bit more as the course goes on, and you'll get a lot of exposure to in Chem 183. For now, you can think about equilibria as a set of temperature and pressure conditions under which a phase of matter is converting, a chemical is being converted from one phase of matter to another, or you have a large relative amount of two or more phases of matter for that same chemical compound under the same pressure and temperature conditions. It means the chemical compound is being converted from a solid to a liquid to a gas, and there's an interconversion happening where you have this phase transition. So the phase equilibrium boundaries are simply the phase boundaries, indicate pressure temperature combinations where that pure chemical will be in transition from one phase of matter to another. A particularly useful phase boundary is the solid-liquid phase boundary. And the solid-liquid phase boundary generally slopes right on a phase diagram, but sometimes, like in the case of water, slopes left. And what a left sloping phase boundary means, if you imagine a straight line up from this point on the water phase diagram here, if the solid liquid boundary points a bit to the left, we call that a left sloping or negative slope between the solid and liquid phase boundary. That indicates that the liquid is actually more dense than the solid, which is a special property that is relatively unique to water and a few other chemicals. Most phase diagrams have a right-facing or right-sloping solid-liquid phase boundary. So in general, when you look at the phase diagram, the first thing you should be struck by is under which conditions you have a solid, under which conditions you have a liquid, and under which conditions you have a gas. What we want to show you first is a simple example of how you interpret a phase diagram, and then we're going to point out other pieces of information that a phase diagram gives you. When reading a phase diagram, it's all about placing an imaginary dot somewhere on the phase diagram that represents the pressure-temperature combination that you're interested in. And the first thing you're generally interested in is whether that dot lands in the solid region, the liquid region, or the gas phase region. So if we're interested in the phase diagram for water, we might ask a question like, what phase does water exist in? Or what phase is most predominant? What phase of water is most stable? Three ways of asking the same question at 1 atmosphere of pressure and 25 degrees Celsius. So if we wanted to answer that question, we would place a dot that corresponds to 25 degrees Celsius on the x-axis and 1 atmosphere of pressure on the y-axis. And we will be unsurprised, because this is room temperature and atmospheric pressure, to see that our dot lands in the liquid phase of water, which is exactly the phase of water we would expect to be most common at room temperature and 1 atmosphere of pressure. We could play the same game and ask about what phase water would exist in if we changed the pressure and temperature conditions and moved to some other region of the phase diagram. But in general, the way you read a phase diagram is you're looking for which phase of matter is going to be most stable, in which region of the graph does your dot land at a specified pressure and temperature combination. So if you're asked about 1 atmosphere of pressure and 25 degrees Celsius, You go up the y-axis to 1 atmosphere, draw a line over. You go down the x-axis to 25 degrees Celsius, draw a line up, and you will see that your dot lands in the liquid phase of water. If we ask the same question that we asked before, what phase does water exist in at 1 atmosphere of pressure and 100 degrees Celsius? We would do the same game, go up to 1 atmosphere of pressure, go over to 100 degrees Celsius, and our dot would land right on this liquid vapor phase boundary, which indicates that water should be boiling, should be vaporizing in transition from liquid to gas at 1 atmosphere of pressure and 100 degrees Celsius. And in fact, it is. That's water's normal boiling point. Where in this case, normal boiling point indicates, once again, that this is the boiling point of the pure compound at 1 atmosphere of external pressure. So that's the basics of how you read a phase diagram. We're going to pause here and then come back in a minute, and we're going to talk about some of the more sophisticated or hidden elements and pieces of information that you can get about a pure chemical compound from its phase diagram. We'll talk more about the significance of the triple point, the significance of the critical point, the normal boiling point, and the normal melting point, and what some of the phase boundaries mean for different chemical compounds. So come back for that in a minute.